We'll start class in just a minute. I'm trying to get something opened up real quick. Okay, everyone. Sorry about the delay. Okay, so exam 3. The average on this exam was a 60.25. I guess good news was that the standard deviation was 17 points, which meant that the class was kind of closer together in terms of the grades. The highest grade on the test was an 84, and the lowest grade was a 20. And I think I just gave a 20 because I'm not sure why. But so yeah, I mean, the class on whole struggled. There's only, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 people that passed. Or wait, 9 above 970 and up. So anyways, I know that there are several of you who are like, if you look at the Canvas and you go look at your grades, there's several of you in here that are like mathematically cannot pass the class anymore, which is a little discouraging. So I'm going to just offer what I've offered to all my classes throughout my teaching, which is when you take the final, if you do well on the final, then I'll let that replace your lowest exam grade. So that's about it though. I mean, I'm not going to replace 2 exam grades with your final. So that means for some of you, the difference between passing or not passing the class is going to come down to the final exam. And, you know, the more I think about this, you know, I don't like it when students don't succeed in the class, but at the end of the day, you have to be ready for Cal 2. That's the way I have to approach this class. And trust me when I tell you that if you barely limp through this class and you have to take Cal 2, you're going to probably wind up taking Cal 2 3 times before you pass it, if you just barely get through this class. Going into Cal 2 as a strong Cal 1 student, an A student, B student going into Cal 2, then you have a good, you know, you have a chance, okay? But Cal 2 takes no prisoners, okay? And I'm not exaggerating that. It is a brutal class. And so it doesn't make sense for you to just barely get through Cal 1 and expect to ever succeed in Cal 2. So my recommendation is always that, you know, if you're a computer science major, engineering major, one of these heavy math majors, then if you're at that borderline of passing this class, for your own benefit, you should just retake the class and try and come out of it as a, you know, with an A, because then you'll set yourself up for success. It's really hard to see students in Cal 2 that can't do Cal 1. I mean, it's just, it's very challenging because there's nothing I can do for them, you know. I can't go back and teach them Cal 1. So if they can't do product rule, quotient rule, chain rule, if they can't do differentiation, they're not comfortable with it, then, you know, Cal 2 is just a nightmare. So anyways, I'm not trying to scare you or freak you out. I'm just trying to be real with you. And at the end of the day, if you're looking at, you're trying to get a degree so you can have a career, right? then one semester, if you have to go back and retake a class, even though that might throw you off in terms of your plan, if it throws you off by a semester or even a whole year, that's small when compared to where you're trying to go. You know, so if you have to go back and retake class, no big deal. You go back, you retake it, and you know, you adjust your life around that. So, okay. So I will replace the lowest exam grade you had with the final. And if you have any questions on, you know, what you would need then to get on the final to pass, you can do the math yourself, or you can reach out to me and I'll be happy to calculate that for you. Are there any questions?
Yes, sir. I was wondering if you ever received my email that I sent you yesterday.
If it was yesterday, what time?
Oh, probably around 4:20.
Yeah, I don't think that I've looked at any emails from that late in the day yesterday today. I've been pretty busy today, so.
Okay.
But I will. Is it something that, is it personal that we can't discuss here, or?
It's regarding the tests, so.
Okay, yeah. All right, I'll look at that email.
Appreciate it, thank you.
Mm-hmm. Anything else? No. Okay, so we're gonna, today, we only have 2 class periods left, right? And then we have our final, right? So our final exam is scheduled for, when is that? Is that Thursday? Yeah, it's this upcoming Thursday, or sorry, not this over. Next Thursday at 12:30, not at 1 o'clock. And it'll go till 3:15. And I've sent out a review. I sent that out the other day for you to start preparing for the test. And my intention is not to give out the answers, although I probably will at some point give you the answers, but I don't want you counting on that. I want you working on it right now, trying to figure it out, asking questions, doing what you need to do to get yourself prepared for the final. All right.
Sir,
Yes.
are we gonna be able to get fully in depth to the optimization problems, or have we already run out of time for?
So we've done some optimization. I haven't done nearly as much as I wanted to. I'm going to start today with an optimization problem, and then we're going to move on to the next section. There's 2 more topics I want to cover in the next 2 days. So I guess to answer your question, not as in depth as I'd like to, but we will, you know, the problem on the final, that's optimization, will be consistent with what I've done here in class.
Okay.
What else?
Yes, sir. For the sections that we are going to cover today or in these next 2 days, are we going to have versions of that on the final, or are we going to disregard that for the final?
What we covered today and on Thursday will be on the final.
Okay.
And it's actually on the review. On the review, it has problems like what I'm going to cover today. The review specifically, here's the review. Basically 14, 15, 16, and 17 are all problems from what we're going to cover in the next day or 2. Okay. All right, so let's start today with an optimization problem. Let's see, today is what, the 4th? Yeah. Okay, so let's do an optimization problem. So this was before the test. We were talking about optimization, right? And the whole idea behind optimization was to try and figure out a way to maximize or minimize something. All right. So we did like a rectangular pen. We did this can that had to hold a certain amount. We wanted the minimized surface area. We did this graph close to this point. This is the one I made that mistake on. And I wanted to mention something about this problem. I was going to do a whole new video on it, But this problem, if you go back and work this out, I would never give this to you on a test. When you try and figure out where the derivative is 0, you get an equation you cannot solve. It's something that we don't know how to solve. And so traditionally in a class where we didn't have a winter storm, I'd have more time in this class. I would actually show you how to solve that equation using the next section in our list of sections. We would use what's called Newton's method. Unfortunately, I'm not going to have a chance to go over Newton's method, but it's okay. You probably won't see that again. And maybe computer science majors will see it, but when you see it, it'll just be an algorithm they give you, and it'll be pretty easy for you to pick up, I think. So, yeah. So we did that. I want to do something new, though. Okay. So I want to do a problem like, see if there's something here. See if there's anything here I really want to do. Come on. I really wanted to do this one, but I'm going to keep it a little more basic. So let's say that we want to build, this goes back to building pens, okay? So I want to put some animals in a pen. And I want to construct the pen as follows. We're going to have 4 identical pens, okay? So 4 identical pens. And we want to build this out of 450 feet of fence. Now, here's the catch. When I have my little animals in these pens, I think I'm gonna put some chickens and I'm gonna put some other animals in here, okay? When I do this, running up along the side of the pens right here, we're looking at the pens from the top. There's this huge river here, okay, that flows through right here. And so my little chickens can come over here and they live in here, and then they can just come up to the edge and they can drink water out of the edge here. So when I build this, I actually don't need fence here along the river edge. So I only need fence, I'll highlight it. I need fence here, 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 and here. This is going to be open. Does that make sense? Any questions there? So I want us to find the dimensions which give the maximum area. So I have 450 feet of fence. I want to make these pens so that my chickens and stuff have enough space. So I want to build them in a way that they have plenty of room in there. It's the most room I could possibly give to them. Because again, I could do this, you know, I could build it this way where I have these pens that are like really, really narrow and really, really long like that. I can have my little pens in here. But my poor chickens would just be like standing there right at the edge of the river, you know, scared all the time. So I mean, there's different ways to do it, right? I could do it this way too, where I make them like really, really long and narrow like that. You know, and then they're just kind of, yeah, that's, so there's some optimal way to do this, right? To use all 450 feet of fence and get the most area possible. So let's do it. I'm going to get rid of these scenarios there. All right, so what is it that we're trying to optimize? We're trying to find the maximum area, right? So I need to come up with some way to represent the area. This is what we called our objective function. And then we're going to have a constraint over here. So the objective is to find the maximum area. So I need to come up with a formula for area, which means I need to come back up to these pens and I need to label them. So how about for the sake of doing this, we'll call this X, that distance from here to here. And now we have a couple of options. We could call this whole distance Y. Or if you want, we can call Y just the distance like from here to here. And then we'll have multiple Y's. So what do y'all want? One big Y or 4 individual Y's? Totally up to you.
One big
One
one.
big Y.
One big one? Okay, we'll do one big Y. Okay, so now in terms of this picture, do you all agree that the area of this is X times Y?
Yes.
Okay. Now, unfortunately, the area is not a function of a single variable right now. It has 2 variables in it, X and Y. So I need to try and get it down to 1 variable. But now I can use the constraint. I have 450 feet of fence. That means when I build this, and that part, I can use 450 feet of fence. So 450 has to be equal to the perimeter. And it's not really a perimeter because it's not the outside. It's all of this, right? So how many X's will I have to build?
4, right? I don't know how to
Five.
count. 1, 2, 3.
5 vertical.
I have to build 5 X's, don't I?
You could do y plus 5x.
Yeah, or the other, yeah, I could say it 2 ways. It's either Y plus 5X or 5X plus Y. So I have to build 5 sides that have a length of X. 1, 2, 3, 4, 5. And I have to build 1 length that has Y. All of that together should use all 450 feet of fence. And then at this point, I can solve for Y by subtracting 5X on both sides. And now come back over here. And now my area should be a function of 1 variable if I replace the Y with 450 minus 5X. And that means the area should be 450X minus 5X squared. So now we have an area function and we want to find the maximum of this, right? So what comes next? It's a very important step.
Quadratic formula. Or
How do we find the maximum of function?
Find the derivative.
Take the derivative, right? Okay, but we're missing something.
The domain.
Yeah, domain, right? So we have to figure out which path we're going down. Are we going to do the closed interval method? Or are we going to do the other way where we find local max and mins? We have to, this is where we have to determine that. So let's look at our domain. X is our variable. Are there any restrictions on how big X can be?
It can't be bigger than, well, it has to be bigger than 0 and can't be bigger than 450.
Okay, yes and no. It has to be bigger than or equal to 0. Do y'all agree with that? Like if I made it 0, then I would use all 450 feet for this side, but I would have, the fence would be all the way up against the water and the chickens would be dead floating down the river, right? But that would be an extreme. X would have to be definitely greater than or equal to 0. I agree with that part, but I can't say 450. Here's why I can't say 450. Because if whatever X is, I have to be able to build it, right? So I have to be able to build this, 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 and this with the fence that I have. So I need 5 sides of length X to total 450, which means that each one would have to be 90.
Yeah.
Right? So the biggest X would be 90. But then I would have nothing left over for Y, right? I'd have nothing left over for Y, which would be the other extreme. So this is a closed interval, isn't it?
Yes.
And because it's a closed interval, I'm going to use a closed interval method, which means I'm going to take the derivative, which is 450 minus 10x. Just take derivative of this. Now I'm going to figure out where that's 0. So you take 450 minus 10x, set it equal to 0. So you should get 4.5 as x if you solve that. I also have to look at where the derivative doesn't exist, but that doesn't happen because the derivative is a nice polynomial. And in the closed interval method, all I have to do now that I found my critical point or critical number is go back to the original function and plug in 4.5, plug in 0, and plug in 90 into the original function, not to the derivative, right? We're not trying to figure out where this function goes up or down because it's the closed interval method. We know that it hits a max and min either at the endpoints or at a critical number. So we're just going to compare them together. So if I plug 4.5 into this, I get 4.5 times 450 minus 5 times 4.5. And that equals something. If I plug in 0, I get 0 times 450 minus 5 times 0. That should be just 0 because I had a 0 out front. If I plug in 90, get 450 minus 5 times 90. That will also be 0 because this is 0. That's 450 minus 450. So it's looking like this has got to be where the maximum is. So I'm going to use my calculator for that. I'm getting 1923.75. This is definitely where we have a max. Do y'all agree? Now, the question asked, find the dimensions. Sorry, this should have said dimensions. Find the dimensions which give the maximum area. So I need to figure out what the dimensions of this pen must be. And what I know so far is that the x has to be 4.5 feet. But what about y? Y is going to be, we come back over here to where we had an equation for y, and we replace the y, replace the x with 4.5. And that will be y. And 427.5.
Yes, sir.
Is that what you got?
Yes, sir.
Yeah, 427.5. So I want this to be 427.5. It seems weird.
So isn't x supposed to be 45?
Was it 45? Oh. I think my brain has shut off. Why did I put 4.5? I knew this answer seemed wrong. Does it seem weird to you to have this be 427 feet long and then for this to be 4.5 feet? It's not going to be a square. It's not going to be a square, but yeah, this is 45, not 4.5. What did I do? All right, well, we have to change that. That's 2 days in a row I've done something stupid. Let's fix it. Okay, this is x is 45. This is 45. This is 45. 450 minus 5 times 40, 45. Okay, so what does that give us?
101.25.
101.25?
Well, that's what I got.
That's what I got.
Yeah, okay. Now that's going to still be our max, but now this is going to change. Our y value is, what is that when we get our y? $450 minus 5 times 225. Okay, 225. Okay, so let's change this. This should be 225.
Yeah, that looks better.
That's better. Okay, and then 45 feet. There we go. All right, that's it. That's the dimensions that will give us the maximum area. And then each one of those, we're done with the problem, but each one of those pins, since there's 4 of these wide, they're each going to be about 56 feet wide. 56.25 is the width of each one of these. That's a pretty big pin for a chicken. I have a lot of chickens. Okay, so there's gonna be like 40 of them in here.
My dad
All right.
spoils our chickens more than me, so.
What's
Your
that?
chickens- Your chickens will be spoiled like ours.
Yeah.
You can have one big chicken, like Big Bird.
Big Bird chicken.
And yeah, one, and they all get their own room.
I don't let my chickens spoil. I usually put them in the fridge or something.
They're not certified happy.
All right, we are moving on. Okay, we could continue to do optimization problems, and they can get very complex. What I'm the most important thing here for you, moving on onto the final exam, is that you're able to read the problem. You're able to, realize you're doing an optimization problem. You're going to write down your objective, write down your constraint. From the constraint, create your function, decide if it's closed interval method or open interval method, and then proceed with the calculus. That's the big thing. All right. Okay, we are ready to move on to the next topic. Almost the end. So we're skipping Newton's method, which again, I said is just an algorithm that I can teach you. This is the algorithm right here that you could code up in some software, and it just helps you solve equations. We're not doing that.
And that won't hurt us moving into Cal 2?
No, you don't need to do Newton's method at all.
Okay.
Okay, antiderivatives. Now this you have to do in Cal 2, like for sure. This is what it's all about, okay? At least the first 1/3 of the class. Okay, so we've spent our whole time in this class pretty much talking about the derivative of a function, right? What's the derivative? What's the derivative? Now we're going to talk about what's called the antiderivative. And let me take you, I'm going to start to give you a glimpse into where we go into Cal 2. So Cal 1 is basically about, well, what do we start with? We start with the limit in Cal 1, then we talk about the derivative. And then there's a bunch of things we do with this, okay? But the whole idea is that geometrically, if in Cal 1, if right now, if I give you a function, f of x, you should be able to somehow go to any point I want you to, go up to that function and find me the slope of that tangent line. The slope of that line is equal to the derivative of that function at x. That's what Cal 1 is about. Someone gives you a function, you should be able to take the derivative. That derivative will give you the slope of the tangent line at any point on the graph. We use that in many different ways to find maxes and mins and things like that, but that's the basic idea of Cal 1. Cal 2, we start talking about this thing called antiderivatives. So the question that we're going to start with in Cal 2 is going to look like this. Let's take a function, but instead of just letting it go forever, let's start it somewhere and stop it somewhere. I'm going to call this first point A. I'm going to call this second point B. And we are not going to talk about slopes of tangent lines anymore. Okay, just throw that away for now. The question is this: can you tell me what the area underneath this curve is? Is there a way that you can tell me the exact area of that? That's a very difficult question. Just generally speaking, that's a very hard thing. And the reason is because the curve, right? If this were a straight line or something, it'd be easier. If it was a rectangle, it'd be really easy, right? So this was like the question that mathematicians were asking, physicists, you know, thinking people at some point had to find the areas of non-standard shapes. I mean, think about if you own some land, right? If you own some property, here's your property. It might be not perfectly straight, right? So you want to know the area of this. Well, how do you calculate it? It's not a nice shape. So calculus is where we actually learn how to find areas of strange shapes. And we start with areas underneath curves. Does that make sense geometrically, what we're trying to do, what we're trying to achieve? Just find that area. Well, it turns out there's really good news, okay? If this function is the function f, okay? If you want to know what that area is, what you're going to have to do is find the antiderivative of little f, okay? If you can do this, if you can find the antiderivative of little f, then you will be able to find the area, okay? But you have to be able to find the antiderivative. And that, you know, the reason it is that way is not easy to explain. That's what's called the fundamental theorem of calculus. There is a theorem in calculus that we call the fundamental theorem of calculus. And what it is a theorem that basically tells you that this is true. But you need to be able to find the antiderivative. So we spend the first third of Cal 2 practicing finding antiderivatives. Find antiderivative, find antiderivative, find antiderivative, right? Once we do that, I'm giving you a glimpse into the class now, kind of going a little off topic, but I think it's worth it. I'll show you something else in Cal 2. Once we do the areas, okay, once we find the area underneath a curve, where the hell is this? Sorry, I'm looking for this here. Okay. So once you find the area, okay, once we get comfortable doing areas, then we start doing things like this. I'm just going to show you a picture. So let's say that we have two functions, right? We should be able to find the area between them using the antiderivative somehow, okay, which that'll be explained in Cal 2. But then we do something really crazy. So imagine that we have this region between these two functions. Imagine now that this actually lives in three-dimensional space, okay? You'll see that? That's in three-dimensional space. What would happen if I took this region here between them and I rotated it around the x-axis like this? Then I would get this weird-looking solid. Right, you'll see that solid. It's kind of hollow on the inside, but it's got a curve to the inside. Guess what my question will be?
What's the volume?
What's the volume of that solid? Okay, that seems like, how in the hell are we gonna do that, right? That seems extremely complicated. Well, guess what? You'll have no hope doing it if you can't do an antiderivative. You have to be able to do antiderivatives to do this, all right? So yeah, that's, then after that, after we do that, those are called volumes, solids of revolution, volumes of solids of revolution. So you take these things, you revolve and you create these solids. Then you have another problem that doesn't seem that hard, but it actually is. What if we were to take a function f, started at A, ended at B, but now just imagine, here's my little thing here. Imagine that this, I don't know if y'all can see this is a little wire. So imagine that this little wire, this cable I have is the function, okay? So here's that function. I'm trying, if y'all can see that. What if I were to take that off the page, straighten it out tight, and measure how long it is? That's called the arc length of the curve. So if you could remove that curve from the page, like take this off the page and straighten it out and put a measuring tape up against it, how long would it be? That question, guess what? You can only answer it if you can find the antiderivative, right? Antiderivatives are an essential tool for doing a lot of stuff in Cal 2. So we spend the first third of the class doing antiderivatives, and it gets harder and harder and harder and harder to do it. But you have to start with baby steps in the beginning, and that's what today is about. I want to introduce you to the idea of the antiderivative, and we're going to do very, very easy antiderivatives. Well, they're easy, they're brand new, so they might seem a little hard, but in the big picture of things, these are the easiest that you ever see. Okay, so here we go. Definition. Antiderivatives. So a function capital F, make this a little bit bigger for you. A function capital F is called an antiderivative of little f on the interval I if the derivative of capital F is equal to little f. All right, what am I talking about? Okay, so if I have some capital F here, we will say that that capital F is the antiderivative of little f if when I take the derivative of this, I get this. So let me start with this. What if little f is 2x? What is the antiderivative of that?
X squared.
X squared. Everyone agree? Because
Yeah.
everyone in this class can look at 2x and realize that that was the derivative of x squared, right? I hope everyone can realize that, right? So you're relying a little bit on your knowledge of derivatives to find the antiderivative here, right? You had to know the derivative of x squared is 2x to go backwards. So Cal 1 is that way, Cal 2 is that way, right? Let me give you another example. What if capital F, I want to know what this is. And over here, I'm going to tell you little f. I'm going to tell you, but again, we're going to start easy here, 4x cubed. What's capital F have to be?
X to the 12.
Is it?
No.
It'll be x to the 4th.
X to the 4th,
Oh yeah, my bad.
right? Now I'm glad you said x to the 12th. Let's write x to the 12th down. Is that correct? Well, what's the
No.
good news? You can check your answer. How do you check your answer? Take the derivative of this. Derivative 12 comes out, x to the 11th. Oh, that's not this, right? So it can't be this. So this is an answer, right? Is that the only answer? At least you're saying no. Give me another example then.
Another example.
I'm sorry?
I'm trying to think, I can't really think of another one, but I know that you probably get another example.
Okay,
Number.
so Elise, let me help you. Let me help you. Let's stick with x to the 4th. But Elise, is there anything that I could put out here that wouldn't change the answer when I take the derivative?
A constant.
A constant, any constant, right? So what if I put +3? Wouldn't this still also be an antiderivative of this,
Yep.
right?
Does that matter? Like, does
Yeah, the constant wouldn't matter, would it? I could do -4. That would also work. Because all three of these, when you take their derivatives, do you see that they all give you the same thing?
Mhm.
So this is an antiderivative of 4x cubed. This is an antiderivative of 4x cubed. This is an antiderivative of 4x cubed. How many of them are there?
Infinite.
An
Infinite.
infinite number of them, right? But I can tell you this, they all have to have an x to the fourth. They all have to have that. Then I can add to it any number I want. I'm going to call it capital C. And this right here is what we call the general antiderivative. Would that have been the same case up here with the previous example? X squared, I agree, is an antiderivative of 2x, but is it the only one?
Notice infinite
No.
as well.
Same thing, right? I could have said, oh, wait, x squared plus any constant. That would be the general antiderivative. Now, you might be saying to yourself, well, wait a minute, this sucks because if I start with the function I want to find its antiderivative, there's an infinite number of answers. Well, there are, but they're all similar to one another. Do you agree that all of these answers look exactly the same, but because you're adding a number, subtracting a number, all it does is takes the graph and like moves it up or down? So like if you were to graph this one, and this one, they would all look the same, except they would be vertical or vertically shifted up or down from one another. Do you all agree with that? That's what adding a number on the outside looks like. So generally speaking, here's 2x, okay? Little f is 2x. That's the red line. One of the antiderivatives of that is x squared, and that's this blue curve. But I could change the value of c and move that anywhere I want, like x squared plus 5.5. That's an antiderivative also. And the reason why it doesn't matter what, where I put it up or down, the reason it doesn't matter is because, yeah, that's good enough. All of these guys, all of them, okay, look at all of, I plotted a bunch of them. What do they all have in common? Look at the slopes of the tangent lines. Aren't they the same? Doesn't matter. Every single one of those functions, the slope of the tangent line is the same, no matter which function you're on. So when we start thinking about antiderivatives, if we start with the function 2x, the antiderivatives are a family of functions. They all look the same. They're just like moved up or down. Was there a question?
Well, going back to the first thing you showed us, like finding the area, wouldn't like going up or down change the area?
Okay, yeah. Great question. No, because you have to see the fundamental theorem calculus first. The antiderivative, we're going to wind up having to subtract two things from one another. And so when you do that subtraction, that's how you account for the vertical up and down shift. Basically, the constant goes away. You're going to be taking that c and you're going to be subtracting that c also. So the c's just vanish away. Stay tuned. That's not going to be in this class. Well, maybe on Thursday, I might give you the evaluation theorem. We'll see. Okay, so general idea. General idea is I give you a function, and then from that, you need to find a function that when you take the derivative of this, you get this. And then you always do plus c because we know we can add a c to anything, right? And taking derivative would just go away. Let me give you another one. I want you to tell me what big F is. Here's little f. Let me help you. There, okay, there. So that's going to be in the answer no matter what, right? But what goes here? What's the function that when we take the derivative of it, we get x squared? Well, what about the power? What does the power have to start at? If we're going to get to x squared, what did the power have to start with?
The third.
X cubed, right? So let's try that, x cubed. Now, does that work? When we take derivative of this, do we get that?
No.
No, because we get a 3 in front, don't we? A 3x squared. We don't want a 3x squared, do we? We want just x squared. So is there anything I can do that would make that 3 not have an impact anymore?
Divide by 3.
Divide by 3. Or if you'd like, how about multiply by 1/3? Wouldn't that do what we want it to do? The 3 would come out, get killed off by the 1/3, that would leave us with just x squared, and there we go. Voila, we got it. Plus c. Are you getting the idea? Okay,
Slightly.
why don't you practice a few of these? I'm going to give you the little f here. And then I want you to come up with over here the general antiderivative, okay? So I'm going to give you a few of them. How about this one? We'll start simple. Okay, 7x to the 6th. Let's do g. Let's go x to the 6th. H. Let's go 1 over x. J. Let's do cosine of x. K, let's do sine of x. L of x. Square root of x. Okay, so I want to know if you can find capital G, capital H, capital J, capital K, and capital L. Let's take a couple of minutes, see if you can do this. The more you know about derivatives, the easier this is going to be. I should also add that what makes Cal 2 a little bit easy is that you can always check your answer, right? Because you can always just take the derivative and check to see if you get it back. Now, if you don't know how to take derivatives, you're in trouble, right? Because then that doesn't work. I'm going to add one more at the bottom. I'm going to go another 2 minutes.
Is this is this where you use the 1 over x plus 1 thing? I mean,
I haven't stated that yet.
Oh,
But
okay.
yes.
Yeah, it is. Okay.
Well, for some of them, not for all of them. All right, I think that's time. All right, I'll take volunteers. You can only go once though. So who wants F? Who has F for me?
I'll take F.
Okay, what do you got?
For that, I have x to the 7th power.
Yes? A little bit more.
Plus 10.
Plus C. Let's always just use C.
Okay.
So I want the general. I'm sorry, I didn't state that. You could have said x to the 7th. That would be a specific example, but plus C is the general, okay? All right, good. Everyone agree? You can check it. Take derivative. You'll get that. You'll get little f. Okay, how about G? Who wants G?
I can take G.
What do you got, G?
Got 1/7 x to the 7th plus C.
1/7 x to the 7th plus C. So Emmanuel had to think through this, that the power here had to go up, right? Because we know when we take the derivative, the power reduces by 1. But he had to account for the 7 that's going to pop out, so he had to kill it off with a 1/7. And that gives us this. Good. Any questions? Who wants H?
I could do
Uh,
H. Oh.
Okay.
Okay, I think Benjamin first. Benjamin?
Natural log of x plus c.
Natural log of x plus c. Okay, so look, everyone. Benjamin, how did you know that?
When you take the derivative of natural log, it's 1 over whatever that is.
Exactly. So you had to know that, right? Like you had to know that from Cal 1. You could. It's not like the previous two where you're sitting there thinking, okay, the power is going to go up here and then I need to kill off that power, you know, right? It's just, oh, I know what the derivative of natural log is. It's 1 over x. Good. How about J?
Sine of x plus c.
Sine of x plus c. And again, you know that because you know the derivative of the sine is cosine. All right. Who wants capital K?
I'll take it. I got negative cosine of x plus c.
Good. Now, most people will make the mistake of putting cosine x here. That's incorrect because the derivative of cosine of x is negative sine of x. We don't want negative sine of x. We want positive sine of x. So we have to put a negative in front of the cosine. And then when we take the derivative, it would give us negative sine, but then negative negative would be positive. So we've got this. Is that clear? Ooh. What about root x? Did anybody get root x?
I got that one.
Okay, Carla, what did you get?
I got 2/3 x to the 3rd power over the like square rooted, all that square rooted.
I'm going to do 3/2. Is that okay?
Yeah, there. Yeah, that's what I got. That's how I did it actually.
Okay, so Carla, did you just think through this? Did you say, okay, this is really like x to the positive 1/2?
Yes.
And then you said, okay, I need my power to go up by 1, right?
Mm-hmm.
You added 1 to 1/2 and got 3/2?
Yes.
And then the 2/3, you did that because you said, oh, but I'm going to need to kill off the 3/2 when it comes out?
Yes.
Yeah, that's it. That's the proper way to think through that. Now, this becomes a little tedious because we're having to think about what the power is and what the number out front is. Maybe we can come up with a general answer for x to any power. So did anyone get this one?
I did.
What did you get?
I got 1 over n plus 1 times x to the power of n plus 1 plus c.
Okay, that is correct. Let's see. Did you know that formula or did you think through it?
I thought through it.
Thought through it. So what was your thinking? You need n to become?
Oh, 1 plus.
Yeah, 1 more than it, right? So using the same logic as before, we know if the power is going to end at n, then in the antiderivative, we need 1 more than that, okay? And then this right here, that's to kill off the n plus 1 when it comes out, right? So this n plus 1, when we take the derivative, would pop out. It would get killed off with this n plus 1 out here. And then we'd subtract 1 from here and we get this plus c. Good. This is an important rule. This is called the power rule for antiderivatives. Not to be confused with the power rule that we learned prior to this. We learned this power rule when we were taking derivatives, that the n comes out and you subtract 1 from the n. That's the power rule for derivatives, for taking derivatives. This is the power rule for antiderivatives. And guess what, everyone? We have a formula sheet. And if you look at the formula sheet, remember that on our formula sheet, we had all the stuff for differentiation, all these rules for differentiation, how to take derivative of things, right? Product rule, quotient rule, derivatives of exponential and logs, derivatives of trig functions, blah, 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 blah. We didn't go through all these. But right after this is something called a table of integrals. Now, we haven't talked about integrals yet, but I want to point out a few things here. Do you see this right here? See where it says u to the n? And then we have u to the n plus 1 over n plus 1. This is basically the power rule. The antiderivative of sine is negative cosine. The antiderivative of cosine is sine plus c plus c plus c. What I'm getting at is later on, you're going to realize that all of these are formulas for taking antiderivatives. So this was all the rules for derivatives. Here's the antiderivative rules. But guess what? They keep going and going and going. So if you actually look in the back of your book, if your book actually does have the formula sheets in it, here's the reference page 1. That's algebra and geometry, trig, special functions, more special functions. Okay, this was the page for derivatives. And then here's where antiderivative starts. Antiderivatives, that's the sheet that you can see on the screen. Here's another page with antiderivatives. Another page with antiderivatives. Another page with antiderivatives. Another page with antiderivatives, and then we stop. So there's a lot more formulas for antiderivatives than there are with derivatives. But in my classes, I only allow them to have the first page. Everything else you have to be able to do. So I guess what's my point? My point is that you're going to have formulas, right? There's going to be formulas that you're going to have and that you're going to use, all right? Okay, so where are we headed with this? Let's see. Do you remember, of course you remember this, that when you were taking two functions and adding and subtracting them, do you remember that when we take the derivative, that you just do the derivative of each one separately? So we have two functions that are being added or subtracted, and we say, hey, take the derivative, then you should just differentiate them individually. That's great, beautiful. Doesn't work that way for a product, right? For a product, we have product rule, and for quotient, we have quotient rule. So I'm going to now give you another little f. And I want us to find capital F. So think about this. Little f is the derivative of capital F. And I have two terms, right? Plus between them. That means we should be able to do the antiderivative of both of these separately and then put those together over here with addition between them. Then we'll do a plus c. In other words, I'm going to find the antiderivative of x, put it here, do the antiderivative of this and put it here. So antiderivative of x, I'm going to do this a little slow. This is really x to the first power, right? So what we're going to need to do is add 1 to that power. And then we're going to need to put out in front of this 1 over whatever that power is, 2. And that will kill off the 2 when it comes out. Any questions on that?
No.
Okay, now the next one, this you can make this hard, you can make it easy. See the 3 in front? Don't let that bother you, okay? Just bring the 3 over. Because remember, when you have a number in front of a function, when you take the derivative, it comes for the ride, doesn't it? The 3 comes for the ride. So I'm just going to take that 3 and do the ride backwards, okay? So we're going to go this way back to 3. And now I'm going to focus all my attention on x to the 4th. So the antiderivative of that, Well, I know I'm going to need an x to the 5th. And then what needs to be out in front of it?
1/5.
1/5. And now I'm going to clean this up a little bit. It's going to be 1/2 x squared plus 3/5 x to the 5th plus c. So now I just put the 3 back on top of the 5. And you can check this for yourself, right? Take the derivative of this and you should get back this. Is this making sense, everyone? Any questions?
C. That's good.
Okay. So how about this? Little f equals 5. What's capital F?
5x.
Yeah, don't overthink it, right? What do you take derivative of to get 5? Well, how about 5x plus c, right? Derivative of 5x is 5. What if this number was, how about this? What if I have f of x equals pi? Well, pi is a number, isn't it?
It's pi plus
Pi.
c.
It'll be what?
Pi plus c.
IX.
Pi x plus c, right? You need the x there because if it were pi by itself, the derivative of pi would be 0, wouldn't it? And so the antiderivative of pi has to be pi x. Here's another one.
Sir, quick question.
Yep.
Do we just put the letter C for constant down for every time we find the
Every
antiderivative?
time you're finding a general antiderivative, you always have to put plus c.
Okay.
Some professors will not count the problem correct if you forget plus c. They'll actually count it all wrong. I don't, in my classes, in the beginning of the class, I don't take off. And as the class progresses, I start to take off if you keep forgetting it. What about this one?
Would
F
this
of
one
x
just be
equals c.
C?
Just c. The antiderivative of 0 is just a constant because a derivative of a constant is 0. Are y'all waiting for this to get harder?
Hopefully not.
Absolutely.
Okay, so how about this? 1 plus x plus the square root of x plus the cube root of x plus 1 over x plus 1 over root x plus 1 over the cube root of x. Okay, that looks terrible, but it's actually not that bad if we just think through it slowly, okay?
Wouldn't we do it individually since they
We
are?
can do it individually, each one, because we have plus, plus, plus. And even if those were minuses, we could do these individually, okay?
Mhm.
But the only thing we really know how to do right now is that power rule. So let's see first, before I do any antiderivatives, let me rewrite this in a way that might be a little more user-friendly. All right, let's see if this all makes sense to you.
Why did you do 1 over x? Why didn't you do x to the -1?
Okay, I'm glad you asked. Why did I not do this one? So like on this, I changed it over to the 1/3, 1/2. This was 1/2 on the bottom, but I brought it up. This was 1/3 on the bottom, I brought it up. And so Austin's asking, why didn't I do this one?
Natural log.
That's the one special one, okay? This is the special one, 1 over x. We need to remember that the antiderivative of that is natural log. Okay, so that's why I didn't switch it. But I'm glad you caught it because I was hoping someone would say, like, why didn't you do that one? All the other ones you changed. So are there any questions on this so far? Like what I've done? I've done absolutely 0 calculus at this point. This is just algebra.
Have made.
I'm sorry?
Natalie.
I didn't hear.
Would it have made it more difficult or something if you were to try and make them all have the same like I don't know, a common denominator.
that would make
it
it a
one
lot-
thing.
That would make it a lot more difficult because they're already separated, right? They're each separated with addition and subtraction. So what we would be doing is putting it together would make it more complicated. We can attack each one of these one by one. Okay, y'all ready? Here we go. Antiderivative of 1. X,
Oh, X, yeah.
right? Okay, this next one has a 1 power. So I know it's going to be x squared, and then I have to put a 1/2 in front. So I'm adding 1 to the power, and I'm doing 1 over that power. Plus, okay, here's where things start to get a little weird. You need to add 1 to a 1/2. So I need to take a 1/2 and I need to add 1. That's 1/2 plus 2 over 2. That's 3/2, right? So this one here, I'm going to have an x to the 3/2. And what needs to be out front?
2 over 3.
2 over 3, right? The reciprocal of this. The reciprocal of this, 2/3. That way, when the 3/2 comes out, it turns into a 1. Let's try the next one. X to the 1/3. So I'm going to have to take 1/3 and add 1 to it. So that's 1/3 plus 3 over 3. That's 4/3. So I know that my answer has to be x to the 4/3. But what has to be out front?
3/4.
3/4. Okay, so just so we're clear on these
So
antiderivatives.
it's pretty much opposite, Professor. In a I mean, right now we used to do negative, like -1, and now we're just adding 1 and plus trying to cancel these off.
Yep.
Okay.
Yep.
Thank you.
Yep. Now the next one plus, now here, what is the antiderivative of 1 over x? We said this was the special one.
Log.
ln x, natural log of x. Plus, okay, now be careful, be careful. The power here is -1/2, -1/2. So we have to do -1/2, and we have to add 1 to it. That's -1/2 plus 2 over 2. That's +1/2. Isn't it?
Yes.
Yes.
So this is going to be x to the +1/2. And with a drum roll, what goes in front?
2.
2.
2. The reciprocal of 1/2, which is 2 over 1, which is 2. One more. Plus, okay. -1/3, we have to add 1 to it. I'm not going to show that one. -1/3 plus 1 is 2/3. And in front, I have to do the reciprocal, which is
3
3
over
over
2.
2. There you go. This was, I mean, you're never going to see a function like this. This was just to give you an example of how, you know, pluses between things, you do them individually. And then this is just a good example of how different powers of x you can do antiderivative of using this rule.
Sir, can I ask a
Yes.
question?
Uh-huh.
So for the antiderivatives of 1 over root x and 1 over cube root of x, could I just do like natural log of root x and natural log of cube root x?
Good. I'm glad you asked that. So what Elise is asking is, let's take a look at just that one, okay? I'm going to do this just separately. If this was our function, question is, can this just be, what did you say, natural log of root x?
Yeah.
Right? So that's the question. Well, let's see if we can answer that question. Let's take the derivative of this. So the derivative of this would be derivative of natural log of something, which would be 1 over it, right? Now the derivative of the square root of x, which we've learned is 1 over 2 root x.
Yeah, I forgot that part.
And if we multiply these together straight across, we get 1 over 2x. But that is not this. So the answer is no, you can't. The only one that is the natural log is the one in green. All the other ones have to be done with the power rule. Good question. Okay, you ready for a new one?
Yeah.
All right. Now, I hate to show students the wrong answer. Okay, but I think in a problem like this, it's constructive for me to show you the wrong answer. So here's the wrong answer. Oh, sorry. That's the wrong answer. What did I do?
You just did the top and bottom individually.
I did
Right.
the antiderivative. Yep, I did the antiderivative of that and got that. I got the antiderivative of that and got that. And then this one, I did the antiderivative. I had to remember that that's x to the half. And then I did the antiderivative of that and got that.
Would you is this like, would you have to do the opposite of quotient rule or something? Isn't
Well,
this a quotient?
We're going to do something. Hold on. Let's not get ahead of ourselves too much here. Do you all understand first what I did, right? What I did, just did each one individually. Now, why is it incorrect? Well, it's incorrect because if I now go to check this and take the derivative of this, what do I have to do?
Quotient rule.
Quotient rule. And the quotient rule is never going to spit this out because the only way this would come out is if you did the derivative of these three separately and just put the answers here like this. If you try quotient rule on this, it's going to be a nightmare. Like it's going to be bad. It's not going to be this. So this is just wrong. Do not make this mistake. So the question becomes, how do we do this? Well, we get lucky in this problem. We get lucky because there's two terms on top and one on the bottom. And because we have two terms on top and one on the bottom, I can split this into two fractions, right? I can do 1 over the root and I can do x over the root. And that now allows me to rewrite those as x to the -1/2 plus x to the +1/2. So I hope everyone's comfortable with how I got this. This is 1 over x to the +1/2, and then I brought it back up, right? We did that on the previous example. This, I just did that this is x to the 1 over x to the half, which is x to the 1 take away a half, which is x to the half. That's just properties of exponents. So that's where that came from. Questions?
No.
Now the antiderivative. Oh, shit. I forgot. Over here, plus c. Remember all this? I forgot to put plus c. I hadn't turned in my test yet, so I didn't get points taken off. Okay, here we go. So antiderivative of this, I need to add 1 to that power. So if I add 1 to -1/2, I get a half. And out front, I have to put the reciprocal, so 2. Plus, now, x to the 1/2, I add 1 to that, I get 3 halves. And out front, I have to put the reciprocal. And then plus c. There we go. Well, what do you think? What do you think?
I'm thinking about what we're going to do for all the product and quotient. backwards
Yeah,
kind
so
of stuff. That's what I'm thinking about, like the
yeah,
future.
so this is now, I think you can start to see that right now I'm being very careful in terms of the functions I'm giving you. Everything I'm giving you, you can get like x to a power plus x to a power or minus x to a power. Or in this case, I gave you a fraction, but you were able to split it into two pieces. Please understand that if I flip that fraction over and I were to have given you this instead, square root of x over 1 plus x, you cannot split that into two fractions because you have one term up top and two on the bottom.
Right.
So if we got that problem, we would be stuck. Okay, and you are just, we're not prepared for that yet. And you would do that in Cal 2 further into the semester. A couple of weeks in, you'd learn how to do that.
Okay, I got a random question. Since there's like an antiderivative for this and whatever, is there like an anti for like L'Hopital in like a
Well,
way?
L'Hopital is not used to take derivatives. L'Hopital is used to take limits.
Limits.
Right? So well, I guess what you're asking is when we do L'Hopital, we do derivative of top and bottom separately.
Uh-huh.
I guess you're saying, is there some version of L'Hopital where you do the antiderivative top and bottom? Is that what you're kind of saying?
Yeah.
No, there's not actually.
Oh, okay. Interesting.
Okay. I'm trying to think of how much I want to do here. Okay, so let's do this. Recall that if f of t, let's do if f of x is a position function, then f prime of x is the velocity function, and f double prime of x is the acceleration function. Now this goes back to when we first were talking about derivatives. We did a couple of examples of this early on in the semester. Said, hey, look, if the f function gives you position, then when you take its derivative, that gives you velocity. And when you take that derivative, you get acceleration. Do y'all remember hearing that? Do you remember us talking about that?
Yes.
And I think we use different functions. I think instead of f of x, we use like d of t. And when we take the derivative of that, we call that v of t for velocity. And when we took the second derivative, we call that a of t for acceleration. So that was the notation I believe we used in class. But the general idea is that if some function gives you position, its derivative gives you velocity, and the derivative of that gives you acceleration. So let me ask you this. If, so this is a new problem. If a of t equals 3t plus 4, find, find v of t. Okay, so I've given you the acceleration function, and I want you to give me the velocity function. So when you look at this up here, what we're basically saying is that if we start with position, take the derivative, we get velocity, take the derivative, we get acceleration. I'm giving you acceleration and I'm asking you to go back to velocity. So we're going to need anti, aren't we, to go backwards? So what would the velocity function be here? So what's the antiderivative of 3t? Remember what to do with the 3?
Yeah.
Bring it
Keep
down.
keep it because it's a constant.
Mhm. T is going to be raised to what power?
2.
2. Okay,
2.
and now in front of that,
1/2.
1/2. Plus, okay, the antiderivative of 4 would be
4x.
4t.
4, I'm sorry, T.
4t. Yeah, it's okay. That's why I gave you a problem with t in it, because I want us to just be careful with the variables. And then don't forget plus c. So there's good news and bad news here. The good news is we were able to find a velocity function, but not exactly the particular one. We just found a family of functions that could all be velocity functions for this. Okay, so that's it. We've done that. Now I'm going to ask you another question. If a of t is equal to 3t plus 4, and I tell you that v of 0, now let's go v of 1 equals, let's make it v of 4 equals 20. Find v of t. So do y'all see that this is the same problem from before? But I'm giving you one more piece of information. So first off, we know v of t. It's this. We did that just a second ago. It's 3/2 t squared plus 4t plus a constant. But now we have another piece of information. The other piece of information we have says that when we plug in 4 for t, the velocity function needs to spit out 20. That means when I take 4 and I replace it into my velocity function, it needs to spit out 20. So I'm replacing the t with 4 here, and the output has to be 20, which should allow me to solve for c. So this is going to be 3/2 times 16 plus 16 plus c equals 20. 2 goes into 16 8 times. 8 times 3 is 24 plus 16 plus c equals 20. 30, 40, subtract 40. I'm getting c is negative 20. Anyone else get that? So let me answer the question. I wanted to find v of t. I'm actually able to nail it down completely. I know v of t must be 3/2 t squared plus 4t minus 20. That's your velocity function. So what am I saying here? I'm saying if I give you the acceleration function and ask you for velocity, you're only going to be able to give me the general antiderivative, unless I provide you with one piece of information. I just have to be able to give you the velocity at one single point. If I do that, you're going to be able to nail down the exact velocity function that we're talking about. So without this information, all you can give me is a family of functions, right? An infinite number of family of functions. But with this one very little piece of information, you can pick out the exact one. Make sense?
Does it matter if the 20 is negative or positive?
Our answer or this?
Well, you said it's supposed to be equals 20, right?
Well, it's 20 here, right? I said it's equal 20, but when we solve for C, we should get negative 20.
Okay.
So I put those two together, got 40, and then I subtracted 40 on both sides.
I have a question.
Yes.
Back at the beginning of this, so scroll up a little bit.
Yep.
So we went from A of t to V of t.
Yes.
That's going backwards, right?
Yes.
So we subtract whenever we were finding the antiderivative. Shouldn't we have added to the, because on V of t you have 3 times 1/2 t squared. Shouldn't that have been 3 times 1/4 t to the 4th? Because we're going backwards, right? So you add, you don't subtract. 'Cause
We went from here to here. Oh, I think what you're doing is you're looking at this number
Yes.
and
Like,
saying add to that.
yeah. I see what I'm doing.
Yeah, no, I got you. I'm glad you brought that. We're looking at the power on the t, which is 1, and we're adding 1 to that. The 3 is just coming for the ride.
Yeah, because that would have to be 3t's squared if it was, right? What I'm thinking. The original would have to be 3.
Yeah. If it was squared, then it would be
I see.
cubed. Yeah. This is actually, believe it or not, this is actually a very profound idea of going from acceleration backwards. So let me see. Does anybody
Question.
remember? Oh, go ahead.
Would the antiderivative of position be just time itself?
Wait, say again.
What would the antiderivative of like the position function be? Just time itself?
Yeah, so that's a little weird. I can somewhat address that question. Let's do it this way. Let me start with this. And this might be a little harder to explain. Okay, let's say that this is time and this is position, right? Then that would be our position function d of t. If we take the derivative of this, I know this is not what you're asking, but just bear with me for a moment. If we take the derivative of this, we get the velocity function, right? Now, what are the units in this? This is still time, okay? And then this axis is now your velocity. And the way you look at the velocity is by looking back here and taking position over time. So this would be position divided by time. Position divided by time is velocity. So this is now the velocity axis and time. Now, if we do the derivative again, now we have time, and now this is acceleration, a of t. And notice that acceleration is this divided by this. Just like this axis was this divided by this axis will be this divided by this. So we get position over time, which is why you've probably taken a physics class or heard this before, that acceleration of gravity is negative 9.8 meters per second or per second squared. That's because you're doing meters is position, time divided by time, meters per second, and then per second again is a second unit of time. Are you kind of following this? So if I were to go backwards, okay, so now what you're asking me is what happens when we go backwards? When we go backwards, what happens? We're basically taking this, right, and multiplying it by time, right, to get rid of one of the times, and that takes us back to this. And then to go back again, we're going to multiply this by time again, and the times cancel, and we get back to position. So Elise, to answer your question, if we were to take the antiderivative of the position function and go back, this would be time, but this would be what? Position, what?
Times time.
Times time. You were asking me what it would be, right?
Yeah.
So if this function, I'm going to have to give you an example. This function gave you like how far you had gone after a certain amount of time. So after, let's say, 1 second, you've gone 4 meters. I'm just making up units here. If I go 2 seconds, I've gone 8 meters, right? Back here, it would be, I don't even have a name for it, so I'm going to call it capital D of t. At 1 second, your answer would be what? Well, you need the antiderivative of this, which would be t squared, 2t squared. Right? Derivative of that would be this. But your answer here would be plug 1 into this. You would get 2, and this is the important thing. What's the answer? 2 meter seconds. Meter seconds. I'm not saying that that has any physical meaning. And you asked me the question, like, what would the unit be, right? The unit would be meter seconds. not meters per second, meter seconds. So
Is
it's a
there
weird
any
thing.
real world application for that?
Not for that, because we don't need to go from position back to anything, because this thing doesn't have a whole lot of meaning. But when we start with acceleration and go backwards, then it makes sense, because acceleration backwards goes to velocity, velocity backwards goes to position. Once you go past that, it doesn't make sense. Also, if you take the derivative of acceleration, keep going to the right, that starts to lose its meaning also. These three are the key ones right here. So, all right, I want to ask you something. How many of you remember this from college algebra? Maybe you remember seeing this function. Or maybe in a physics class or something. Anyone, do you recognize that at all? Maybe?
I've seen it before.
I've seen it before, but I don't know how to use it anymore.
So what this is this is a function that tells you where an object would be on Earth if you were to drop it from a certain height, or if you were to throw it up into the air and let it come back down. So this is basically this is called the falling body or the falling object function. So like if I took a rock, here's a cliff. I'm going to throw the rock off. I'm not going to throw myself off. I'm going to throw the rock off. Okay, the rock is going to go down and fall, right? If this cliff started, let's say, at 400 feet, right, then I would plug in for D0, I'd plug in 400. And then I'd have to plug in the V naught. Now, V naught would be whether or not I threw the ball or the rock up into the air, I let it go, or I threw it down. Those are like three different situations. I could throw the ball up, it would go up and then come back down, or I could just let it go, it would just drop, or I could throw it down, it would go down a lot faster. That's this number, which I'm just going to say, I'll put 20 here. That means I threw the ball up. I threw it up and then it starts to come back down. This gives you the position after a certain amount of time has gone by of that rock. And this works on Earth. Now, check this out. This is a position function, right? Let's think about Earth for a moment. When you drop an object on Earth, what's the only force acting on it?
Gravity.
Gravity. Let's take air out for a little bit. Okay, just gravity, right? What is the acceleration of gravity?
Then
You have to know.
9.8.
9.8.
Negative 9.8
9.8, yeah.
meters per second squared. That's the acceleration of gravity. That's the acceleration at every point in time. Gravity is constant. It doesn't matter when you let it go. There it is. Now, for the sake of ease, I'm going to convert this from 9.8 meters per second into feet per second. This is negative 32 feet per second per second. Okay, so all I'm doing is converting from meters to feet. So check this out, everyone. This is an acceleration function on Earth. So acceleration is negative 32. Check this shit out. Give me the antiderivative of this. What's the antiderivative of this? So what's the antiderivative of the constant negative 32?
32x.
Negative 32. I'm going to use t, but yes. Plus what?
C.
Some constant, right? Okay. Let's take the antiderivative again. Take the antiderivative. The antiderivative of this should give me the position function. Okay, the antiderivative of negative 32t is negative 32 times, I need t to the half and or t to the 2.5 in front, right? Plus the antiderivative of a constant, which I don't know, it's just the constant times t, plus some other constant that I don't know. And guess what this is?
Oh my God.
That's this formula. Except instead of V naught, that's some constant. Well, that's C here. And instead of D naught, that's just D here. Which means this. You go to any planet in the universe, if you can measure the acceleration of gravity, then you can always come up with a position function for that planet. all you have to do is take the antiderivative twice. And you can then drop an object on the moon and be able to predict exactly where it's going to be at every moment in time. Simple antiderivative twice. And not only that, would you agree with this? If you're on a planet that has constant gravity, like Earth, right, or the moon, then do you agree that your position function will always be quadratic? If you start at a constant, the first time you take the antiderivative, you're going to get a t. The second time you take it, you're going to get a t squared. And so every planet can be modeled, you know, dropping an object on any planet can be modeled with a parabola for any planet. Now, assuming gravity is constant. I don't know of any planets that have non-constant gravity, but you can imagine that perhaps a planet could. If maybe the core of the planet was liquidish, like a liquid form, and it's moving around, and so the density is changing, and so maybe the gravity wouldn't be constant. But for all intents and purposes of what we do, right, we first have to get to another planet. But I guess what I'm trying to get at here is that it may seem like a miraculous sort of like, wow, this formula is just, oh my gosh, we can tell where an object is at any point in time. Like, oh my, wow, it must have taken like just this huge hurdle to figure this out, right? There's no hurdle. It's just two antiderivatives. That's it. That's all it is. Okay. So it's not that miraculous. Now you do have to know how to do a little bit of calculus, but okay. We're almost out of time. I still have 3 minutes. I want us to consider something to lead us into our last day of class. I want us to look at this function. I'm going to start with capital F. Okay, I'm going to start with capital F. And I'm going to write down sine of x squared. Now, give me little f. So this is what we've been doing all semester, okay? Give me little f. So take the derivative of this.
Is this chain rule?
Yep, chain rule. So you get cosine of x squared
times 2x.
2x.
I'm gonna put the 2x in front. Okay? Y'all agree that the derivative of this is this?
Mhm.
Okay, now, act like you didn't know that. And now I'm going to start the problem out. Find capital F. Do you see how this is not going to be that easy? Because we don't have pluses or minuses here, right? We know the antiderivative of this, right? The antiderivative of this is just sine of x squared. That's what it is, because we created it, and now we're acting like we didn't know that. So how do we get back from here to here, right? How do we get back? Do y'all see the inherent problem here? Yes? Okay, so
yeah, because it looks like a.
well,
It looks like a
it's
product
not
of-
x to powers, and it's not pluses and minuses, right? So look, we only have 30 seconds. I just want to kind of plant the seed for next class. I want you to look at this expression, and I want you to see in it that if you squint your eyes just properly, I do see something here, x squared, and I do see its derivative. Okay, do y'all see that the derivative of x squared is 2x? Y'all see that?
Yes.
So what I'm going to do is I'm going to make a substitution in the problem. I'm going to replace x squared with u, okay? With u. So when I rewrite this problem, it's going to be cosine of u, all right? But the question is, what do we do with this? What does that become? Okay? And that I'm gonna have to leave for next class. Because think about it this way, what's the antiderivative of cosine of u? What's the antiderivative of cosine of u?
Negative sine.
Negative sine.
Careful, not the derivative, antiderivative,
Oh,
Fine.
sine of u,
Kind of you.
right? Which is kind of this answer, isn't it, up here? That's kind of sine of, remember, u was x squared. So, all right, we're gonna leave that for tomorrow or for Thursday. What I would suggest you do for homework is see if you can work the problems from 4-7 antiderivatives. See how they go. You may have questions. All right, everyone. We're calling it a day. If you want to discuss your grades with me or anything like that, I recommend